So now let us try to learn a trick to remember the Maxwell's four relations. The relations give us an expression, or the relations are involving namely the thermodynamic variables S, P, T and V, that is entropy, pressure, temperature and volume. The four relations can be easily remembered by using a simple technique. We have to write the four variables in a given sequence. Let us say if we write it as S, P, T, V. Now just recall or note that we have written it in a clockwise notation, clockwise orientation. So SPTV is written in a clockwise orientation. So just remember that clockwise implies positive. Similarly, we can do this way and write SPTV. So this at this place we begin with S and we maintain this sequence SPTV, whereas here we maintain the sequence SPTV while writing from S, but now this is anti-clockwise. So this should be negative if this one is positive. Now just take ratios of these quantities and introduce the partial derivative signs. Then put an equality sign, and clockwise implies positive and anti-clockwise being negative, put a minus sign here. This is how we have constructed two of the four Maxwell's relation. But remember, this derivative is partial. So since derivative is with respect to v, here we are going to take t constant. T appears here, so should be placed here. Similarly, this derivative is partial with respect to t, so we are going to keep volume constant. Similarly, here derivative is with respect to p, so t is kept constant, and here derivative is with respect to t, so p is kept constant. So these two relations were written by starting from S, and S is written in the upper left corner. Now let us try the same thing by writing S in the lower left corner. So S can be written here, and if we go clockwise, we write it as SPTV, and if we go anti-clockwise, we write it as SPTV. We have to do similar thing. Introduce the derivative sign, take the ratio, and then here, since it is a S on the right hand side, we keep S constant here and equal to sign. Here we have P, so we keep P constant here. Similarly, dou T by dou V keeping S constant is equal to dou P by dou S keeping V constant. But remember, this was written in anti-clockwise manner, so we have to put a minus sign. So this is how we can write the four Maxwell's relation easily. So clockwise is positive, anti-clockwise is negative. We always maintain this sequence SPTV. Once we keep S in the upper left corner, then we keep S in the lower right corner. This is how we can write the four Maxwell's relations. Now let us try to derive an important relation called as Clausius Clapeyron equation. Basically, this equation explains us how the temperature or some The temperature corresponding to a phase change. How does that change with respect to change in pressure? That is, suppose at room temperature and pressure, which is the standard values 1 atmospheric and 27 degrees Celsius. We take water and we start to provide heat to it. It begins to boil. It begins to boil at 100 degrees Celsius. That is known as the boiling point of water. But what happens if we change this pressure? It is observed that if the same experiment is carried out at a different pressure altogether, then the water boils not at 100 degrees Celsius but at some different value. So what happens whether if the pressure rises or pressure falls, whether there is a rise in temperature or a fall in temperature, that has to be discussed. And that relation between the change in temperature with change in pressure corresponding to a phase change is given by Clausius Clapeyron equation. This equation can be derived in many ways. We can follow the Carnot cycle approach as well. But here we are going to use a Maxwell's relation to derive this equation. So let us just begin with one of those equations. Dou S by dou V at constant temperature is equal to dou P by dou T at constant volume. Now multiply both the sides by T to get T dou S by dou V equal to T dou P by dou T. Now we note that ds is dq by t. This means dq is tds, right? So this can be used here, and we write dou q by dou v at constant temperature equal to T into dou S by dou T at constant volume. Now the left hand side is just the heat liberated or absorbed at constant temperature with respect to change in volume. So this is a very peculiar quantity. It says that the temperature remains the same, the volume changes accordingly with the change in heat. So there is a substance, its temperature is fixed, it absorbs some heat, and what happens is that its volume changes due to this process. Or the other way, if it rejects some heat, its volume changes, either increases or decreases. That will be further discussion. But this process is possible only when this is nothing but a phase change. That is, suppose we have 1 gram of ice. If we supply heat to it at a temperature, it gets converted into water. So ice at 0 degrees Celsius gets converted into water at 0 degrees Celsius. This is called as phase change. So the temperature remains the same, but the volume of this material changes. So this quantity dou Q by dou V at constant T is nothing but the heat absorbed or liberated per unit change in volume at constant temperature, and it is related to a phase change process. And we know that the amount of heat change or the phase change is nothing but the latent heat. By definition, latent heat. If the substance melts, it is the latent heat of fusion. If the substance evaporates, it is the latent heat of evaporation. Let us say that dV is just V2 minus V1, that is the change in volume. So V1 is the initial volume and V2 is the final volume after the change in heat has taken place. So the left hand side, dou Q by dou V at constant T can be replaced by just L upon V2 minus V1. Similarly, on the right hand side, we have this quantity T into dou S, sorry, the other thing. So we are left with L by V2 minus V1 is equal to this quantity, yes, T into dou P by dou T at constant volume. So if we rearrange this T can be shifted to the denominator on the left hand side and we get dP by dt equal to L upon T into V2 minus V1. So this is the required expression which gives us relation between change in pressure and change in temperature. This can also be written as dt by dP is equal to T into V2 minus V1 upon L. It's just the same thing inverted. Fine. So this equation can directly give us by how much amount the temperature corresponding to a phase change changes when we are provided with the change in pressure given the values of latent heat corresponding to that phase change, the value of temperature at which the phase change occurs, and the change in volume corresponding to that phase change for the given substance.